Okay, welcome to the presentation part 5. This will actually cover acids. All of this is coming out of chapter 7, but collectively for the naming and formula writing, it's really its own presentation, its own thing, because the method we are using, the Stevens, which uses this type 1, type 2, and for today, type 3 and 4, actually type 4, the acids. Is not mentioned in your book. However, when we're done, we should be able to name all of the same compounds and write all of the same formulas that your book teaches. But this is just a different method of how you group the rule sets together for a lot of consistency. Previous presentation, we have covered types 1 and 2 and 3. We also covered hydrates in the type 2 presentation. And today we're going to talk about the acids, and this is type 4 according to Stephen Zumdahl. And we're going to cover both types of acids, which are binary, where you have hydrogen combined with a nonmetal, so just two elements only. And the what are called ternary acids, where hydrogen is combined with a polyatomic ion, which of course then is more than two elements, thus the term ternary. And we'll cover both of those today. Okay, of course, we're not doing the student learning map, but there you go. It's an important question and important key learning. If we were doing a test, this might be a very good source of a test question or 2 or 3 with modification. So the lesson question here. And type 4, here we go. So while all acids are covalently bonded, we are actually going to treat them as ionic for the purposes of formula writing, because these elements or these compounds do actually create ions under many circumstances, which makes them have the acidic properties that they do. The more ions that they can form, the more acidic they are, and the more reactive they are under a wide range of chemical circumstances. So it's very interesting. However, just the compound itself, it is covalently bonded together, so sharing electrons. Okay, we'll cover first the binary acids, so just type 4 binary acids, hydrogen combined with another nonmetal. Two elements only, binary. Okay, so if you want to go to the formula, or from the formula to the name, what do? Well, first of all, the acid will always begin with the prefix hydro, and it will always end with the suffix ic. So hydro something ic, right? The nonmetal, which is combined with hydrogen, right, will be named with the ic, not ide like chloride. Now it'll be named chloric. So that's how we're going to differentiate it as an acid. So in the case of HCl, hydrochloric acid, hydrochloric acid. So, and then we always tack on the word acid to make sure that it's very clear that this is an acid. Okay, what about name to formula? Well, always, if you have a name and you know it's an acid, we will begin the formula with hydrogen. And then we will record, in the case of like hydrochloric acid, you would then record the nonmetal second. So hydrogen first, the nonmetal second. You would assign oxidation numbers to both elements as if they were ionic. So hydrogen's always a +1. The nonmetal, hopefully you have memorized, -3 for group 15, -2 for group 16, -1 for group 17. Assign the oxidation numbers and crisscross if necessary. You will never have a chance to reduce because hydrogen is a +1. So when the 1 crisscrosses down, you can't reduce anything at that point. So just if they +1, -1, cancel them, go with the formula. If it's a +1, -2, +1, -3, you got to crisscross. Okay, so getting right to examples here, we have HCl, H2S, H3P, HI. So, of course, we want to come up with the names for those. So, because they're all binary, we would always start with the word hydro. Then we're going to take the nonmetal, chlorine, sulfur, phosphorus, or iodine, and we're simply going to change the ending to ic. So, chloric, sulfuric, phosphoric, iodic, right? So anyway, with that, and then tack on the word acid at the very end. So hydrochloric acid, hydrosulfuric acid. For some reason, they stuck the UR back in there. They didn't call it hydrosulfic. They call it hydrosulfuric. A little bit confusing, but it's one of those that once you get comfortable with it, that's the way it is. Likewise, with the hydrophosphoric, they kind of keep the phosphor, they keep both syllables, and then just the ending they use the ic on, which kind of makes sense. And then iodine, becomes iodic. So hydroiodic acid. And then we have the formulas down here, or the names that we would want to develop formulas for. So with that, let's go to a handwritten page, and we can talk about how these came about. Okay, so in the first four, this just explains what we just went through, but of course now you can see the answers. So, first of all, HCl, right? All binary acids begin with the word hydro. It's a prefix, so here's hydro. All nonmetals end with the ic ending, so that's where the chlorine becomes chloric, so hydrochloric acid, HCl. Very common acid, very strong acid, very dangerous acid. In this case, they all begin with hydro, so see, hydro is all right here. And then sulfur becomes sulfuric. They didn't really drop an ending. They just added the suffix ic to it. That's the only one really that I'm aware of that they do that for. Everything else, there is an ending change. In this case, hydrophosphoric acid. And then in this case, hydroiodic acid. Okay, let's move on and talk about how to write formulas from the names. All right, so here are 3 of those examples from that previous slide. So I had hydronitric. First of all acids begin with hydrogen. So I wrote hydrogen down and I assigned the positive 1 charge to it. Nitric comes from the element nitrogen, a nonmetal. Nitrogen has a 3 negative charge. Well, the 1 and the 3, because we're going to treat it as ionic, do not cancel, so of course I crisscross. When I crisscross, I drop the positive and negative signs, and now I have subscript H3N. For every 1 nitrogen, there must be 3 hydrogens. When this groups together, we call it hydronitric acid. I forgot the word acid up here. That's the final answer right there. Okay, with hydroselenic, well, hydro is the hydrogen, so there's hydrogen with a positive 1. Selenic comes from selenium. Selenium is Se with a 2 negative charge. The 1 and the 2 do not cancel, so I crisscross, and then H2Se is the final formula. For hydrobromic acid, beginning with hydrogen, positive 1. Bromine is a group 17 element, so it's a negative 1 ion. 1 and 1 cancel, so it's just HBr. So there we go. There's your final answer there. This is the typed answer key that I normally have because we can work them in class on the board. So there you have that. How we got these answers, of course, has been previously indicated on the last 2 slides. Let's move on to the ternary acids. Okay, here you go. Type 4 ternary acids where hydrogen is going to combine now with a polyatomic ion. Okay, so things to know. If you have a formula and you want to name it, never, never, never use the word hydro. Hydro tells a scientist, tells anybody that knows, that it's a binary acid, and these are not binary, so we can't use the word hydro. That's often confused. I have a lot of students who will start using hydro everywhere, or never use it when they should, so be careful with that. Okay, so never use hydro in the name. The polyatomic ion in the formula, see, hydrogen plus polyatomic ion. The polyatomic ion is going to drive the name. It's going to create the name of the acid. And there are 2 polyatomic ion ways it can go. There are polyatomic ions that end in ite, phosphite, sulfite, nitrite, that kind of thing, right? If it ends in ite, we're going to change the ite to an OUS. So ite becomes us, and then we say that's the acid. So something us acid. So a hydrogen combined with a phosphite polyatomic ion, we would take the phosphite, change it to phosphorus. Again, for some reason they stick the 4 in there. So phosphorus, and then acid. So phosphorus acid would be H3PO3. That would be the formula. If the polyatomic ion, on the other hand, ends with the ending ATE, like phosphate or sulfate, nitrate, oxalate, there's a lot of them that end with ATE, we will change the 8 to an ic. Now, this will not be confusing with the other types of acids that will use the prefix or the suffix ic, because they all would begin with the word hydro, and none of these will. So, hydrochloric acid and chloric acid, two very different acids. Even the formulas look very different from each other. Of course, they both have chlorine in them, but other than that, they are very different. Okay, let's move on. Okay, so name to formula. Begin the formula with hydrogen followed by the polyatomic ion from the name. Remember that acids named with the OUS suffix are going to be the ite polyatomic ion. Acids named with the ic suffixes are the ate, ate, polyatomic ion, so you'll need to just remember to make that transition. Here again, I cannot emphasize enough, and I will continue to do this. If you memorize these ions front and back, I know it's a lot. It looks like a lot. It's actually not as much as you think. But if you memorize them, this stuff can go so quickly. It's not a case of having to look on the back of that sheet for the 50th time for the 50th problem because you can't remember what nitrate is. So I strongly recommend you really, really memorize that. Unfortunately, COVID, this is one of the disservices that COVID is doing for you. Even though it's a lot of work, it would be so beneficial for you moving forward in your chemistry potential classes in college. Okay, then after you put the hydrogen down and you put the polyatomic ion down, you assign oxidation numbers, and if the oxidation numbers do not match, then you crisscross them. If they match, you cancel them and rewrite the formula. You can't reduce any of these because of the positive one of hydrogen crisscrossing, so nothing will ever actually reduce. Now, never change a polyatomic ion's formula under any case. So just remember that. Never change a polyatomic ion formula anyway. Okay, so let's get right to the examples. Here we have HNO2, and then we have HNO3. Now, if you're aware of that, NO2, if you have them memorized or if you look them up quickly, NO2 is nitrite, I-T-E. NO3 is nitrate, A-T-E. SO4 is sulfate, PO4 is phosphate. Then down here we have four names of acids: sulfuric acid, sulfurous acid, phosphorus acid, and oxalic acid. Ic, us. So that's going to tell us what polyatomic ions to use. Notice, no hydro anywhere. Don't use it. Don't use it. Okay, let's move on to some handwritten notes on how to do this. Okay, here I have my first example of HNO2. Well, the NO2 is going to drive the name, so down here I'm saying, okay, NO2 is nitrite. So I'm going to change the ite to us, so it becomes nitrous acid. Nitrous acid. In the case of HNO3, NO3 is nitrate, ATE. So I'm going to change the ate to an ic, and this becomes nitric acid. Nitrous acid is a somewhat weak acid. Not as reactive, not as harmful. I mean, it's still dangerous, right? It's an acid, but not as dangerous as nitric. Nitric acid is a real major concern. It's a very strong acid, major concern. Very pungent odor. If we spilled a lot of nitric acid in the school, we'd probably have to evacuate the school. It's one of those things. It's that bad. Okay, then H2SO4. Well, SO4 is sulfate. If you've got it memorized, wow, it goes that quick. If you look it up, well, you can look it up, but wow, how much time did you have to take to look that one up? Well, the 8 becomes ic, so sulfuric. Here they're going to tuck the UR back in, so sulfuric acid is the name of that acid. Then down here, the H3PO4, well, PO4 is phosphate, ATE, therefore the ic goes onto it, and here they're going to put the 4 back in, so phosphoric, so phosphoric acid, sulfuric acid, right? Let's move on to the other examples. Okay, up here at the top, sulfuric acid. Now I have a name and I want to go to a formula, so let's see what we know. Because it's an acid, it begins with hydrogen with a positive 1 charge, right? So down here, H1 positive. Sulfuric came from sulfate, so SO42 minus. I just dropped that down here, SO42 minus. Positive 1, negative 2, they do not cancel, so I crisscross. That gives me a formula of H2SO4. Or, if you prefer H2SO4, it's the exact same formula, but here I have left the parentheses intact around the polyatomic ion. That is not a crime. You can do that if you want. If you really prefer to keep all polyatomic ions grouped with parentheses, by all means, please do so. But do not put any unneeded subscript outside of those parentheses to the right of them, because then that starts to multiply this as a unit and make a bunch more that you probably don't need. So be careful on that. Okay, sulfurous acid. Sulfurous. Well, because it's an acid, it begins with hydrogen, +1 charge, right? So there that is. Sulfurous comes from sulfite. So SO3, 2 negative. I brought that over here. +1, 2 minus, didn't cancel, so I crisscrossed, giving me a formula of H2SO3. And if you prefer the parentheses, it would look like that. But that's sulfurous as opposed to sulfuric. Here again, the more oxygens in an acid, the stronger the acid is. Now, the oxygens don't make the acid an acid. It's the hydrogens that make it an acid. But the oxygens hold on to everything so much more strongly because of their electronegativity, to invoke some earlier chapter terms, that then causes the hydrogens to be easily lost. These hydrogens easily being lost in a solution make the solution acidic. And the more oxygens, the easier these are lost, the more reactive the substance is. The fewer the oxygens, the stronger the hydrogen is bonded to this, and so not as many hydrogens break off to become the acid. So this is a weaker acid, Okay, phosphorus, and that's always true because between an ic acid and an us acid with the same polyatomic ion system, that the us acid is always going to be weaker. This is just general information. It's not testable for this unit. Phosphorus acid, okay, so it begins with hydrogen. There's my hydrogen with a +1. Phosphorus must have come from phosphite, and so that's PO3. Think about it. I didn't, I have it memorized. There you go. You wrote it down. You don't have it memorized. You're looking it back up again for the 100th time, right? So, H1 plus, PO3, 3 minus, they don't balance, so of course I've got to crisscross them, and I end up with a formula of H3, PO3, or if you like the parentheses, it would look like that. Oxalic acid. So here's a polyatomic ion we haven't had many examples with yet. Oxalate, right? Oxalic comes from oxalate, so it begins with hydrogen, +1 charge. Here's my oxalate, C2O4 with a 2 negative charge. They don't cancel. I forgot to put the crisscross in, but they crisscross, and that creates H2C2O4, or with parentheses. Notice 224. Do not reduce. Do not reduce. Do not reduce. You cannot alter the oxalate polyatomic ion formula. So if you try and reduce this and you start messing around with this 2 or this 4, it's no longer oxalate on paper. And there's no way to get it back somehow as far as reverse engineering your reduced answer to create this acid again. So it would just be an incorrect formula at that point if you reduced it. So be careful. You will never reduce acids, just like you will never reduce the other covalent type 3s. Okay, one more slide, I think. Yeah, here this is again just the type set of answers that I would normally have in class, because we would be working all of these on the board together, or you would be working at your desk on these examples, getting ready for the type 4 homework.